Hello everyone. Today, I'm going to talk about our work OCTR, an Octree-based transformer for 3D object detection. We first give a concise summary. Adopting transformer in 3D object detection encounters the problem of the limited receptive field or the limited representation, which is caused by high-resolution feature map requirement. Inspired by the Octree data structure, we propose an Octree-based attention mechanism in a parallel manner. Specifically, we construct an octree from a common hierarchical feature pyramid, using the attention matrix scores as partitive criterion. In addition, we adopt semantic positional embedding to combine the semantic information of the voxels. We achieve state-of-the-art performance on Waymo and KITTI dataset, and get improvements on pedestrian, cyclist classes, and distant objects. More details refer to our paper or poster. Then we introduce our work in detail. Owing to long-range dependencies and dynamic aggregation, there have appeared an influx of transformers in natural language process and computer vision. However, regarding the usage in 3D object detection, it is unrealistic for transformers to operate on the sparse feature map with the high resolutions. Thus, to avoid the dilemma of heavy computations, it is significant to make transformer efficient. There have some approaches that attempt to tackle long sequence as input. Some methods sparsify the attention matrix by fixed patterns, like local, dilation or Windows patterns. However, they both only achieve bigger local receptive fields rather than the expected global ones, and computations still increase rapidly with the expansion of receptive fields. Another alternative is to take advantage of a proxy memory bank which has the access to the entire sequence tokens. Generally, the number of global proxies is limited, which impair their representation. As discussed above, we propose our Octree attention mechanism which captures rich global context features by a global receptive field in a coarse-to-fine manner while reducing the quadratic complexity of vanilla self-attention. We first describe the overall pipeline of our proposed method. We voxelize the point cloud into regular grids and adopt the sparse 3D convolution for patch embedding. We sequentially stack two Octree transformer blocks, tailed by a downsampling layer. Finally, we project the features into BEV and adopt one or two-stage head for detection. We then introduce the Octree transformer block. Despite it being resource-friendly, the Octree representation is discrete and non-differentiable, which motivates us to alleviate cumbersome pre-processing division by introducing a novel Octree-based attention mechanism. Using a partitive criterion of attention scores, we prune the dense attention matrices of the multiscale feature pyramid to sparse Octree attention in a top-to-bottom manner. It is worth noting that we perform global receptive field on the top layer. When propagating from top to bottom through the pyramid and reaching the bottom level, we indicate selected regions by selecting the top K attention scores as its most relevant token group and then uniformly sample limited attending octants from the selected regions. The above process is run recursively until reaching the bottom level of the pyramid. To fully leverage the local 3D shape patterns and original voxel coordinates, we propose a hybrid positional embedding to capture both the geometry and semantic clues. Specifically, we first segment foreground grids using the supervision from the ground truth. We embed the center coordinate and the semantic score with the feature in a gridwise manner, namely semantic absolute positional embedding. Besides the semantic clues implicitly used in SAPE, we employ the semantic attention mask on the attention matrices to address correlations between inferior queries and superior keys. We compare OCTR with state-of-the-art approaches on the Waymo open dataset validation split. It can be seen that we achieve newly state-of-the-art performance on all the three classes. In particular, for pedestrian, we outperform PVR-CNN++ by a large margin, which indicates the effectiveness of the proposed model in handling hard examples. We additionally report vehicle detection results by distance. As shown in the left table, our OCTR achieves the best MAP among all these convolution-based and transformer-based backbones, which indicates that OCTR has the advantage in capturing long-range fine-grained context. We summarize the performance on the KITTI test set in the right table. With the help of the multi-scale backbone features and rich global context, one can observe that we rank the best or the second best in all the cases. About the ablation study, we acquire sound improvements compared to different detectors, highlighting its scalability. We also compare our Octree attention mechanism in an apple-to-apple manner and analyze the effects of different components of semantic positional embedding, showing its effectiveness. In addition, we add more results of resource costs to clarifying our efficiency. As shown in this picture, our approach precisely predicts both locations and orientations of 3D objects in distant, showing our advantage on capturing long-range ability. Contact us via email if you have any questions or ideas. Thanks for watching.